Alright, today on the bench we have this nobelicious instrument. What is it, Ken?
It's like a Wheatstone bridge on steroids with more branches than you can shake a stick at.
Aha, very funny, Master Ken. But there is truth in that. This is a very improved version of a Wheatstone bridge, an instrument that is used to measure resistance to a very high degree of precision. This one is particularly good at measuring very low resistances. The manufacturer calls it a double ratio set, but it is better known as a Kelvin bridge. It is yet another brilliant invention from Lord Kelvin, who first described it in 1862. Lord Kelvin came up with it when he was trying to characterize cable resistance for the first transatlantic telegraph cable, and was running into trouble while making very low resistance measurements with a conventional Wheatstone bridge. As we will see, he came up with a very clever solution. Our instrument is made by Leeds and Northrup. Leeds and Northrup was formed in 1903 after Professor Edwin Northrup joined a company started earlier by Morris Leeds, located in Philadelphia. The pair quickly made a name for themselves in Wheatstone bridges and potentiometers used for precision measurement of resistance and voltage in the early days of electricity and telegraphy. Collectors still prize the beautiful instruments with wooden cases and black bakelite tops, sprinkled with beefy knobs and shiny brass contacts. That speaks steampunk technology, if you ask me. Refined versions of these instruments persisted into the 1980s, used mostly in calibration labs. Our instrument is no exception, from a Navy calibration lab and decommissioned in 1992, if we believe the tags. There is scant information about the 4398 bridge, but one source dates it as 1965. Our version is the facelifted 4398-M, so maybe it's from the late 1960s. It looks expensive, because it was. It was listed as $3,625 in the 1972 catalog, which would be a staggering $28,000 in today's money. This catalog page, which by the way is the only primary source document I could find about this unit, tells us that it can reach a precision of 0.2 ppm in direct substitution mode, that is, when comparing two resistors of the same nominal value, and 10 ppm when measuring an absolute value. I stumbled upon it in the attic of the Mare Island Museum, which is shutting its doors. Mare Island is a former naval shipyard in Vallejo, California, and is in the midst of being redeveloped. I came in on short notice to help move a horde of military tube radios, teletypes, and X-ray equipment, which had accumulated in the museum's leaky attic. To the joy of the museum, my tube-loving friends not only purchased most of it, but offered to haul it away from the hard-to-access attic. The stuff was so heavy and so damaged that we had to triage what was worth salvaging. And for some reason, no one showed any love for the dusty L&N bridge. To my untrained eyes, though, it looked in much better shape than the tube stuff that my friends were feasting on, and of manageable size and weight, for a boat anchor that is. So I took pity on it and hauled it away.
This is a rescue, by the way, and I saw this one was covered with dust, and I recognized the Wheastone bridge from Leeds and Northrup, which is the kings of Wheastone bridges for a long time.
So what's a Wheatstone bridge exactly? In its simplest form, it's an arrangement of 4 resistors with a sensitive galvanometer in the middle. You power up the whole thing with a low voltage battery. The first branch, RARB, forms an adjustable voltage divider. The second branch forms another voltage divider. This time, RS is a calibrated resistance standard. Rx is the unknown, the resistance you want to measure. Both RS and Rx are usually mounted outside of the instrument, connected via the binding posts. At first, the 2 voltage dividers will be out of balance, and the bridge galvanometer will deflect one way or the other. You then adjust RA using the knobs on your instrument until you return the galvo to 0. At this point, the dividing ratio of both branches is the same, that is, Rx over Rs equals Ra over Rb. The bridge is said to be balanced. Simple math gives you the value of the unknown, Rx equals Rs times Ra over Rb. The key advantage is that the result is independent of the battery voltage. The second key is that the galvo doesn't need to be calibrated, nor even linear, it just needs to detect a 0. Early on, sensitive optical galvanometers like this one were used, featuring a small moving mirror suspended on a wire on which you did shine a ray of light to observe the mirror's slightest movement. They were very sensitive and also a Lord Kelvin invention. The guy just invented everything. But what's up with our instrument? There are far more knobs and connecting posts than you would expect in a Wheatstone bridge. The main rotary switches are named A ratio. Okay, that must be RA, the precision adjustable resistor in the Wheatstone bridge. Makes sense so far. There is also a B ratio knob. Apparently RB is also adjustable in large steps in our bridge. This enables to measure something that's a multiple or a submultiple of the standard resistor RS, up to 10 times bigger or smaller apparently. That's a nice extra feature that was present in the more expensive bridges, which ours sure is. But then we have 2 more knobs labeled LB and 4 more labeled LA. And a yoke adjust button, which is a 10-turn pot without any graduation, and a 2-position switch called lead balance, and a detector push button, although there is no detector in sight. And between the front and the back panel, there are 13 binding posts with mysterious labels. We have some kind of seriously tricked out bridge here.
And I was like, okay, I understand that. There's a readout here for one part of the bridge, but then there's another one here, and there's another one there, and there's another one there. wait, it's way too many. And then we turn it around, and there's all these connections here, which they are labeled. I put bigger labels because we couldn't figure them out. So that was a little bit of a mystery.
And there was no manual.
No manual, no documentation whatsoever. But it says double ratio set. So that was the clue that got us started. So we eventually figured it out by just beeping the connection. Ken, you started that. I was going to open the box saying, no, we just measure the resistance between all the combinations of wires and terminals, and I ended up with something like this. So I have like all the combinations, and we figured out in the end that the bridge was something like this. And what it is, it's the same, it's a Kelvin bridge, but they have added 2 refinements.
Oh my, we'll need more elevator music to untangle this heap of precision resistors. So in the previous elevator ride, we were contemplating this pleasantly symmetric Wheatstone bridge arrangement. However, things are more complicated in practice because the resistors Rx and Rs are wired outside of the instrument, and because lead wires have the nasty habit of not having a perfect zero resistance. So to accommodate our external resistors, we rewire our connections like this. Now, the reason there are 2 different wires going to each resistor is that you do not want any of the Rx branch current to travel in the measurement leads. The first wire connects the resistor to the battery and carries most of the current. It is aptly named the current lead. The second wire connects the resistor to the bridge. Since it carries little current, it transmits the potential appearing at the resistor accurately, despite its residual resistance. It is aptly named the potential lead. Now, if you are still following along by some miracle, you might have noticed that we have a similar but even tougher problem for the galvo connection on the red wire in between the 2 resistors. This red wire is called the yoke wire. It carries the full Rx branch current, and its resistance will impair our measurement, particularly for the very low resistances that Lord Kelvin was trying to characterize. He quickly figured out that attaching the galvo in the middle of the wire, like it is shown here, was messing up all of his measurements. He also knew that if he attached it on the bottom resistor, he'd make the problem worse. All the yoke resistance would show up as if it were added to Rx. Similarly, if he changed it to over here, it'd make it worse in the other direction. Kelvin therefore reasoned that there must be an ideal point somewhere along the yoke wire that should zero out the effect of the yoke wire resistance. And you might have guessed where it is. It's the point that divides the yoke resistance in the ratio Ra over Rb. You can intuitively understand and prove by calculation that if you do that, the yoke wire resistance has no effect at all on the measurement. Both Rx and Rs are increased in just the correct proportion so as to not unbalance the bridge. Great! Problem solved! But how do you locate this ideal point in practice? Plus, you would need to tweak it each time you balance the bridge. And that's where Lord Kelvin's genius invention comes in, the double bridge. He added two resistors, Ra prime and Rb prime, which are the same value as Ra and Rb. That is equivalent to putting the galvo connection at the perfect voltage tap-off point on the yoke wire. It's very clever. The yoke wire resistance effects are completely gone, no matter the bridge setting. Lord Kelvin was then able to measure all kinds of materials for the transatlantic cable, and this double bridge was named after him. But where were we? You can probably recognize that our instrument is vaguely a Kelvin double bridge, but there seems to be even more to it.
It's a Kelvin bridge, but they have added two refinements. Lead compensation, and the second is fine yoke adjustment, the yoke being this wire in the middle that we were trying to eliminate.
Oh no, Leeds and Northrup went a step further than Kelvin, so you must keep on riding the musical elevator for more explanations. One of the practical issues with a Kelvin bridge is that Ra prime and Rb prime are never perfectly equal to Ra and Rb. So to eke out the last bit of precision, Leeds and Northrup added one more trick. They made Ra prime and Rb prime a hair short, 0.25 ohms short to be exact, and added a fixed 0.5 ohms resistor to compensate. They then connected the galvo to a 10-turn pot across the 0.5 ohms resistor, repeating the Kelvin trick but at a finer level. This is essentially a triple bridge now. And that's what our 10-turn yoke adjustment knob is all about.
The yoke thing is a fine adjustment of the yoke to get the last bit of adjustment.
While they were added to make things easier, Ra and Ra prime as well as Rb and Rb prime are mechanically connected together on the same knob. So they always change in lockstep. There is no separate knobs for Ra prime and Rb prime. Which leaves us with two unexplained series of knobs at the top of the instrument. We had shown how the lead resistance influence can be reduced by using multiple wire connections to the resistors. But this only minimizes the problem. To eliminate it completely, you add small resistors in the A and B leads until the lead resistance ratio is the same as the Ra over Rb ratio of the main bridge. At this point, as was the case with the yoke, the lead resistance has zero effect on the measurement. The small variable lead resistances are called La and Lb in our instrument, which explains this series of knobs. In order to find a correct ratio for the lead adjustment using the bridge itself, it has to be rewired a bit. And that's what the last refinement is for, the lead balance switch. It simply shorts out Ra and Rb. We'll see later how that works in practice. So, phew, finally we can identify all the knobs and all the binding posts, and voila, you have the Leeds and Northrup double ratio set fully explained.
And with that, you have something that has 7 decades. if you look at the one furthest to the right, it's 0.1 ppm, right? Which we'll see is very hard to achieve. I want to show you how it's done inside.
Yeah, I want to see what's in here. Oh, wow. Look at all those twisty resistors.
You like it? So these are the lead adjusts, so they are fairly low values. And then you have the main decayed resistor over here.
Yeah.
They're mirrored, right? So that's for
So you have
RA and RA prime. That's RB and RB prime. And interestingly, you see all those wires that are cut and go to nowhere?
Yeah, that's wild.
And I think it's just the calibration, right? When they make the thing.
Yeah, I guess you wouldn't want to unsolder them. But looks like there's more extra wire than you'd need. Why wouldn't you just cut it off closer to the...
Yeah, I have no good explanation for that, except that this must be during manufacturing, right? This is not somebody has taken something out, and then they don't desolder them; they just cut them. And I suppose this is not regular soldering; it's cadmium solder.
Tasty.
Low, they are the best. Low EMF. It's just lots of resistors. So
They look more like inductors.
yeah, all wire wound with special whatever. So that's one of the 0.01 ohms lead compensation. 1 ohm, 0.1, 0.01, 0.001, and that one is continuous. It's a wire. Whee! In extra 0.5 ohm resistor. That's this 0.5 ohm here.
So is this the battery positive negative switch?
Yes, that's the battery reversal.
Mm-hmm.
So you're supposed to have it work on both sides.
So because with EMF you might have different current. One
Exactly,
direction versus the
to
other.
get the EMF out of it. EMF being the voltage that appears at contact points when two different metals join.
Mm-hmm. Everything turns into a battery.
Oh man, I discovered that big time. We'll probably find out pretty soon. X is for 10, but you're not supposed to do that. You're supposed to go to 9 and then up the next one. It is RB in fixed ratio, so you can only measure a resistance that's 10 times bigger to 10 times lower than your reference resistor. Right, so it's a fairly narrow range for a given reference resistor. That's the yoke, that's to do the lead balance, reverse of the battery, lead A, which is a coarse one, no, lead B, which is a coarse one, and lead A, that's where you have the 0.0001 adjustment. So to hook this thing up, it's a whole adventure. First, I have to do battery, because it flows straight through your resistor, so you have to be a little careful. The usual voltage is 1.5 volts or less. Most of the current goes into the resistor measurement branch.
But the actual voltage doesn't matter for the measurement.
Yeah,
It's
yeah.
only for the valve.
And then D2 and D1 are measurement. You need something that goes into the microvolts to get to the 7th decimal over here.
This later generation instrument was expected to be connected to a sensitive electronic detector, not with an electromechanical galvo. It is shown here with the model 9828 null detector that was supposed to go with it. It included very sensitive electronic amplification. We don't have one here, so we'll press my trusty HP3478 DVM into service. It goes down to 100 nanovolts sensitivity, which should get us there.
And then comes the fun part. You need a reference resistor. New to my collection, they just arrived, so I haven't tried them yet. So the big ones, they are Russian. says CCCP on it. 1991, 1964, and 1984. So it's the coil is in between those walls in that cylinder here, and then you have the four wire setup. So I have a 10 ohm, a 1 ohm, and a 0.1 ohm, and I have also the Leeds and Northrup reference resistors, 1 ohm, which I just bought, and 10 ohm, which looks like a knockoff for a Leeds and Northrup, but sold by somebody else, rebadged. So can you want to explain how these are supposed to be used and why they have so many weird connections to them?
Well, you can either put your 4-wire connections here, or you can dip these two ends into little pools of mercury and make your connection through the liquid mercury.
Yeah, so the primary way of measuring the resistance is actually with a little mercury cup through that, but we're not going to use that.
You don't want to try the real mercury? Makes things more interesting.
I'd have to ask Ben, with all the chemical, and you have to make an amalgamate. You have to put some sodium into the mercury.
Yeah, what could go wrong?
Yes, they tell you, and why you mix them? Don't look at it. Look away from it. I understand why. Anyhow, we won't be able to get to the 0.1 ppm, except for comparing. But these are precise to 10 ppm only. Mm-hmm. I don't have a primary standard. So we'll at least be able to compare what they are. Oh, and you see the wiring here. First I made some little lugs and all good stuff, but you can't. It introduces EMF.
So you want everything in copper?
Yeah, so you want everything in copper. CS, so that's the battery sense 1, sense 2. So that's a 10 ohm. Should I compare measure my Russian resistor? Okay, let's do it with my decayed resistance box first, because I have a hookup for that. It's going to be easier. Battery sense 1 and sense 2, yoke wire. So plus resistor wired across those two, minus resistor wire across those two, and the yoke wire between the two resistors. To get our bearings, let's start to measure 10 ohms versus 10 ohms here. That's going to be the easiest. Okay, so we are going to do a 1-to-1 ratio. So this is at 100 ohms and this is at 100 ohms. Put it at 0. Then the maximum current here is 250 milliamps, and that one should be, so maybe we'll current maximize it at 160. Why I am at plus 1.8 volt DC, because I should be approximately in balance. Because the detector button is not pushed in. All right. Better. Okay, so I'm at minus. Oh wait, because LA and LB right now are. I should put them to the same thing. I'm starting with LA and LB equal to 1 ohm, so that's my lead resistor compensation. I am at plus something. And I can make it negative. Okay, so cool. I'm slightly above 10 ohms. And so I'm going to get to a ref balance. So I'm 1.001, so that's pretty cool. Those two resistors are pretty close. Okay, so I'm going to move that one down to pretty close to 0. Okay, so that's here somewhere. And the first thing I need to do is to adjust the lead balance. This thing over here that puts you in lead balance. So now you're measuring LA and LB versus RA prime and RB prime, which I have already adjusted about right. So I'm pretty close already. I have to add 0.1 ohms. 0.2 ohm is too much. About right here, right? The lead imbalance is 0.017 ohms. Okay, so now I'm in balance with the lead, so I redo a measurement. It has thrown it off a little bit. I wish I had an analog meter here. So that's about correct. So I go back to lead balance and it's slightly off. So it takes forever to get a good measurement. So now back to measurement, and well, I'm still good. 10 ppm is about as good as we should get. And I can make one more adjustment, which is the yoke adjustment. And for doing that one, it took me a while to figure that out, is you unplug that, and now you have an infinite yoke, and that magnifies the effect of the yoke adjustment, and I know that. Okay, so now I'm yoke adjusted, and I go back and do the adjustment again. Right here.
And then you need to do the lead adjustment again?
You just need to do the lead adjustment again, but it hasn't moved very much, right? So now we're... So it's so repetitive because you do all this bridge adjustment, so everything is exactly the same ratio. So you get the main one, then the secondary one, the tertiary one, and then you go back and hopefully you convert. So now my lead is correct. My measurement is very close. It tells me that this resistance box, actually compared to this one, is 10 ohms. So 10.07777. 10.07. So it's
0.8% off?
Yeah, about, yeah. 0.8% off.
So if you do the battery normal reverse, is everything still in balance?
Actually, no.
Or should I not open up that can of worms?
No, it's not, and actually I should not, I've done it wrong, because I should not have balanced it on the 0. I should have balanced it on the average of the 2. See, it goes minus 75, minus 20, no, plus 24, minus 74. So what I should do is, actually, if you want to refine that some more, is you want to find something where the two numbers stay the same. Minus 70 plus 18. Let's try to balance it around minus 27. There you go. So that's my real 0 when it's the same in normal and inverse.
So that's to counteract EMF that appears.
So we have to redo the whole thing now, trying to balance it at minus, what was that, minus 25. I'm pretty close. Okay, yeah, that's the direction. So we are 1.00779 instead of 0.777.
Well, we got a little more accuracy out of it.
Yes.
That makes it all worthwhile.
Yeah, but it's just so much knob and turning and finger poking. So it tells us 1.0078. Let's try to see what the HP meter tells us. So the HP meter also has a Kelvin clip. Guess what it tells us in a fraction of the time? 1.008. So they basically agree. But that's with 10 ohms. It starts to diverge where you go below 0.1 ohms. then this gets completely off kilter. You just can't do it. We haven't done it justice actually, because where it's really good is that if you do direct replacement and very low resistances. Okay, so now I've wired myself up to do 10 ohms Yankee versus 10 ohms Russian, and it should be 10 and 10. Okay, they're 1.999. Oh, I switch it off. Russian and Yankee agree.
To what precision?
This one is slightly lower than this one, so I had to put it on a ratio of 2. If they were equal, it should read 2.00000. It reads 1.99993, which is better than spec. It's 10 ppm. Oh, you know what? That might be part of my problem here. This has slipped. Yeah, it's even closer than that. It's 1.99995.
Well, that's pretty good.
So you divide it by 2, and they were within like 2.5 ppm of each other, which is pretty good. And that I'm not able to measure on the, forget it, the HP won't tell me this. Alright, so boop, boop, that should be 10 ohms. It tells me 10.0022. But I don't know how much I would trust this last decimal. 10 ppm, it should be 1, 2, 3, 4, 5. Yeah, so it's way better than this. So I don't believe the last 2 decimals on the HP. Since I have just bought a 1 ohm Yankee, let's try the 1 ohm Yankee versus the 1 ohm Russian. Alright, round 2, Russian versus US, and once again, this is not that temperature bath. Contact preparation was limited to the offset, so this is by no ways a valid measurement. Okay. Yeah. 1.99975 on the 2 settings, so I have to divide this by 2. This one is short of the other one by 12 ppms. Alright, let's do the more difficult one, which is going to be the 0.1 ohm. Get some 2000 grit. The offset. I do need to have 10 to 1 lead balance. There we go. That's starting. So you have to, when you change the ratio here, your lead balance changes too, right? So now I have to be 10 to 1 on B. Measurement. Oh yeah, pretty close. Okay. Yeah, normal. So when you are at low resistance, EMF gets you, right? It just starts to grow and grow and grow and grow on you. So if we think this one is 1 ohms, this one is 0.10019. Yeah, 0.2%. That looks far off. I would expect a much closer match. Let's see what HP thinks about this one. Boop, boop. This one reads it low, but this indicating 10019, and I rechecked the 0.1 ohm resistor with using the Russian counterpart to the 1 ohm resistor reference, and I come up with the same result, 0.10019. This number is correct. I don't trust the number I get on the HP. I think this is the correct one, which is very far away from what it should be, right? I should have a 0 here and just a 1 over here, or a 2. So that leads me to believe that this is actually, this has drifted from its 1964 value. Even standard resistors, they drift. You have to calibrate them every few years, and for sure every 60 years, right?
Alright, that was a lot of knob and turning, although I realized that I did it wrong, or at least the complicated way. The standard procedure is to do one measurement with the battery connected one way, then do another one with the battery connected the other way, and do the average of the two. That should be far quicker. That said, let me show you one more very useful feature of the LNN bridge.
Also, let's not forget one more application to this box. If you use it between RL and D1, you have access to this resistor over here. So right now it's at 100 ohms plus a small offset. And if I want to add 200 ohms, here we go. 210 ohms, 220 ohms, and I can go a step of 1 ohms. So it's super precise. The offset remains, but it's super. The delta is very precise, which is why it's so precise in direct comparison. So now I can add 0.1 ohm at a time, and here 0.01 ohms at a time, and then 0.001 ohms. I tickle the last decimal on the meter, and then 0.001, which you won't see. And also you have access to LA between X1 and RL. So I have to move this one to X1. Same thing, you'll have a small offset. It's 1.0005, but you can do 2 ohms, 3 ohms, 4 ohms, at 4.1, 4.2, 4.3, 4.4, and now I'm going to add 0.1 ohm, 0.01 ohms at a time. Let's make it 5 ohms exactly. That's right, 9. 5 ohms. So it can serve as a very fancy decade box of resistor.
Well, that's it for now. I learned not to trust my HP ohm meter when it comes to the last decimals, and to trust my 60-year-old Soviet standard resistor even less. Mind you, at least said resistor has now been recalibrated, so I can trust it again for a few years. On top of that, the Leeds and Northrup makes an incredible 7-decade resistor box. Mostly, it has the most clickalicious knobs of any instruments I own. But don't fret if you don't own one of these, since using an HP DVM in 4-wire mode is good enough to test resistors to 0.1% in a fraction of the time, but a fraction of the style too. See you in the next episode!